Section 6.1, Roots of Real Numbers. The objectives here are to find the roots of real numbers and to determine correlations that exist among the different types of roots. First, let's take a look at a square root. And a square root is really defined as the solution to the following equation: x squared equals some constant. And for the sake of this, we'll say that constant is b. And what we'll notice is that if we want to solve this equation, there's going to be two solutions to this: either radical b or negative radical b. And what we'll see is that there have to be two answers because this is x squared. And we'll notice that there are two answers here. This is called the principal square root. Again, the positive root of this is called the principal square root. And we'll notice that if you square a number, whenever you square a number, it comes out to be a positive answer. Pick any number, even a negative number to start with. So that means that b has got to be greater than 0 for there to be real solutions. Alright, part A says to simplify, and we're going to look here. We're just going to take a look at the principal square roots. So when we see a square root, you want to think, well, what two numbers, when multiplied, and the number being the same, gives you 4? Well, it's just 2 times 2. That's what gives you 4. So therefore, that means that the square root of 4 is simply 2. The next part here, we're going to see that we have the negative square root of 16. So we have to think negative. Well, the square root of what number times itself gives you 16? Well, that number is 4. If I put a 4 here and a 4 here, I get that 16. So this answer just becomes 4, but we have to carry down the negative sign, so the answer here is negative 4. And then finally, the square root of 9/25. Well, if we take a look at our rules, we could say, well, that's radical 9 over radical 25. And the square root of 9 is 3. The square root of 25 is 5, and therefore we have 3/5. In example 2, we're asked to find the real roots of each of these equations, and if there are none, to state that. So let's take a look at example A. If we solve this by thinking about factoring like we've done in the past, what we can do is start by saying, well, x squared minus 25 equals 0. Where does that come from? We subtract 25 to this side. Now, at this point, we can factor this because this is a difference of two squares. So this becomes x plus 5, x minus 5, giving us roots of x equals negative 5 and x equals positive 5. And these are our two answers. And if you think back to earlier, we had in the equation x squared equals b, and we said the answers are radical b and negative radical b. Well, here's radical b, right? Radical 25 is here, and then negative radical b shows up here. Again, though, there are two answers when we solve this equation because it's x squared. There have to be two answers. Another alternate way to do this, though, and it might be quicker, and once you pick up on this, it's pretty easy, is to realize, well, if you have x squared equals 25, you just take the square root of both sides. So square root both sides, and we realize that, well, x is equal to 5, but when we take a square root and it's an equation here, we have to remember that we're looking for two solutions, so it's plus or minus 5, which is the same answer as these two that we got earlier from the other method. Part B, x squared plus 49 equals 0. Well, we could start this problem by saying, can you factor it? And right away, it's tempting to say you could, but x plus 7 doesn't work because you're missing the middle term. So we could start by moving the 49 over and say, well, x squared equals negative 49. But a moment ago we said that for the answer to be real, this has to be positive. Because when you square a number, when you square some number x, it has to be a positive answer. So no matter what we put in for x, no matter what real number, we'll never get negative 49 out. So as a result, we can say that there is no real solution. For part C, we could take a look and start by saying, well, we could try and factor this. We could factor out a 4, leaving behind x squared minus 5 equals 0. But that might get a little bit messy. Let's pause for a moment and go to the alternate solution method first. And if we do that, what we'll see, for this alternate solution, let's move the 20 over. We'll get 4x squared equals 20. Divide by 4, giving us x squared equals 5. And then we have to take the square root of both sides. So the answer for x is simply going to be radical 5, but we have to remember it's plus or minus radical 5. So that's what our solution is going to be via this alternate method. Well, it's the same solution we would have got, technically, because really, you can factor this. It's difficult to factor because this is not a perfect square, but in reality, we could think of it as a perfect square. We could write this as 4 and then x plus root 5, x minus root 5, and that equals 0. And therefore, if we were to solve this, we'd get x equals negative root 5 here, and x equals positive root 5 here, really the same answers that we got for this alternate way of solving it. So if you remember that when you're solving an equation that's x squared, if there's no linear term or no x, you could just get the number on this side, the constant by itself, and then take the square root of both sides, remembering that you have two answers, plus or minus. Similar to a square root, the cube root is the solution to the equation x cubed equals b. And for these, there's only one real solution to this equation, and it's denoted by the cube root of b. Okay, this means the cube root of b. So let's take a look at a few examples to understand what's going on here. We're going to treat these just like we treated a square root. For a square root, you asked yourself what number times itself gave you the radicand. Now you need to ask yourself what number under here times itself 3 times gives you the radicand. Well, that answer in this case is 3, because 3 times 3 is 9, times 3 is 27. So the answer for the cube root of 27 is simply 3. Okay, again, whatever number appears here, because that number will repeat itself. Well, what about the next one, you might say? Well, there's a negative under here. So we're looking for the cube root of negative 8. Well, 2 times 2 is 4, times 2 is 8, so that means that these must all really just be negatives. And let's take a look. Because it's tempting to say, well, this is imaginary at first, or this is not real, as we've seen in the previous examples. But what we'll notice here is that negative 2 times negative 2 times negative 2 is indeed negative 8. Because this gives you positive 4 times negative 2 gives you negative 8. So this is simply negative 2. In the next example, we're going to see here that if we're looking at 10 to the 6th, well, the way we're going to break that into 3 numbers that are the same is by thinking about the fact that this 6 here can be broken down into 2, 2, and 2. We can write it like this. And that's simply because, if you remember your rules of exponents, when you multiply 3 things with the same base, you add the exponent. So 2 plus 2 plus 2 is what gives you that 6 right there. So the answer to this question is just 10 squared. Again, all you do is take one of these and bring it down as your answer. Just take one of these and bring it down as your answer. And again, 10 squared is obviously 100. Now for part D, what we're going to notice is if we want d to the 12th to appear, and that is a result of the product of 3 variables or 3 expressions that are the same, we'd have to break this into d to the 4th, d to the 4th, and d to the 4th. Again, appearing 3 times, because this index is 3 here. This is the cube root. So we take one of these and bring it down as our answer. And what you'll notice is that in these last 2 examples here, if you take this 6 and just divide it by this 3, you get 2. Well, that's what the answer was that we had. If you take this 12 and divide it by this 3, you're going to get 4, the answer that we had there. And this works, but the question becomes, well, what happens if this exponent is not divisible by whatever this index is here? And we'll see that in a later section. Now what we want to do is generalize. We want to say, well, the nth root is defined as the solution to the equation of x to the n equals b. And the solution of this is equal to the nth root of b. The nth root of b. Now, n, this little value here, is called the index. In the previous part, we looked at when this was a 3, and we said it was the cube root. Well, the square root is really a 2 there, but we just don't show it with square roots. But if you want like the cube root, or the 4th root, or the 5th root, you have to put a different number here to indicate that. The value that's underneath here, under the radical symbol, is called the radicand, and again, this symbol is called the radical. Let's take a look at a few examples here. If we look at the first one, we're going to see to ourselves, well, what number times itself 4 times gives us negative 16? And it might be tempting to say negative 2. But you'll notice that if you do negative 2 times negative 2 times negative 2 times negative 2, you end up getting positive 16. Again, this gives you 4. 4 times 2, or 4 times negative 2 gives you negative 8. But then negative 2 times negative 8 gives you a positive 16. So in this problem, negative 2 doesn't work. 2 clearly doesn't work, because 2 to the 4th is also 16. So there's no real solution here. But what about part B? Part B, we're going to see here that we have the 5th root of 32. So we have to say to ourselves, what can go in here 5 times to give you 32? Well, it's just 2 times 2 times 2 times 2 times 2. That appears 5 times. Our answer is just one of these values, so our answer is indeed 2 for part B. For part C, we have to say what quantity times itself 4 times gives you x to the 20th. Well, that's just x to the 5th. And I can see that because x to the 5th times itself 4 times, you add up the 5s, you get 5 plus 5 plus 5 plus 5, giving you x to the 20th. Or just simply take this 20 and divide it by 4 to give us a 5 there as x to the 5th. Finally, part D, and part D is a little bit confusing. I'll do it down here. We want the 5th root of negative 1. Well, we have to come up with a number 5 times that gives us negative 1. Well, it's just negative 1. And you could check. Negative 1 times negative 1 is positive 1, times negative 1 is negative 1, times another negative 1 is back to positive 1, positive 1 times another negative 1 is back to negative 1 here. So the answer is just one of these, and it happens to be negative 1. So the conclusion that we can draw is the following. If the radicand is negative, we have two possible cases. A negative radicand with an even index is no real solution. But a negative radicand with an odd index has a real solution, and all it is it's going to be just the 5th root or the nth root of whatever that happens to be with a negative sign tacked on. For example, just to make it clear, if we had the, say, 3rd root of negative 125, well, that's just going to be negative 5. And that comes about because the 3rd root of 25 is just 5, so the 3rd root of negative 125 is indeed negative 5. So we're seeing here it comes about from this. Okay, and that's the exact same thing as what's up there. Okay, this here is the same thing as the expression below. So the answer happens to be just, again, one of these, negative 5, because negative 5 times negative 5 times negative 5 is negative 125. So again, to generalize, if the index is even and we have a negative radicand, then there is no real solution. But if the index is odd and we have a negative radicand, there is a solution, and that solution just happens to be a negative answer, as we see right here. Finally, example 5 says to determine the values of x so that the expression represents a real number. And we'll get a real number in these problems when the radicand itself is either 0 or positive. So it's any of our whole numbers. So we have to set this greater than or equal to 0. Because again, under the radical you could have 0 or you could have a positive quantity there. So by setting that greater than or equal to 0, we just solve for x by adding 3 to both sides. So x must be greater than or equal to 3. And that's part A. And try it. Pick any number that's not greater than or equal to 3. Try 2. Well, if we plug a 2 in, 2 minus 3 gives us negative 1. Well, that's a non-real number. Well, we want a real number here. So part B is going to be the same thing, but a little more complicated. So again, we're going to set the radicand greater than or equal to 0. Well, this is now a quadratic inequality, so we must factor this in order to solve. Factoring into x minus 7 and x plus 4, giving me critical points of x equals 7 and x equals negative 4. These are the critical points in this problem. If those are the critical points, we start by making a number line, negative 4 and 7. These are going to be closed circles because it's greater than or equal to. And then we have to test points in the regions. Test the point like negative 6. Negative 6 in here is going to make this negative. Negative 6 in here is going to make this negative. Negative times a negative is a positive. Then we pick a point in the middle region. We could pick a point like 0. Make it easy. Plug in 0 here and here. That makes that negative, makes that positive. Negative times positive is negative. And then we'll pick a point over here like 8. 8 minus 7 is 1. 8 plus 4 is 12. 1 times 12, well, that's still positive. And in this problem, we wanted to know when the inequality was greater than or equal to 0. So the positive regions are the ones we're going to shade. So we shaded to the left there, and then we shaded to the right over here. Now that gives me a solution set in this problem of numbers less than or equal to negative 4, or numbers greater than or equal to positive 7. So if you try any of those numbers in that radical that we had for part B, you'll end up getting a real number as an answer.